So we know small atoms like hydrogen can only accept one bond, but bigger atoms have more valence shells and can accept more bonds than just four. So they can have more than an octet. And expanded valence shells are observed only for nonmetal elements in period 3 and beyond. I'll show you what that looks like on a periodic table. So on your periodic table, this is period 3, and anything from phosphorus on, that's a nonmetal, can accept expanded valence. Remember, the noble gases don't really bond, but strangely enough, we can actually get krypton and xenon to bond. So if you want to make a list of the ones that will do this on your paper, anything below row 3 that's considered to be a nonmetal can accept expanded valence. So let's take a look at a few examples of expanded valence. Phosphorus has 5 valence electrons plus 5 times 7. So that's going to be a total of 40 valence electrons. So think about who's going to go in the middle in this compound. And the least electronegative is phosphorus, so it's going to go right in the middle. Then you want to spread out all those chlorines around the outside. So 1, 2, 3, 4, 5. All right, let's draw one bond between each. 1, 2, 3, 4, 5 bonds. So that's 2, 4, 6, 8, 10 electrons that we've used up so far. So we have 30 left to go. So here we go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. Everything's spread out. Everybody has an octet. Phosphorus has more than an octet, so phosphorus is the one with expanded valence. So if you want to make yourself a little note of that, you can. Alright, I'd like you to pause the video here and try the structure for sulfur hexafluoride. Sulfur has 6 plus 6 times 7, and that's a total of 48. Sulfur will go in the middle. Now you guys know a lot about fluorine and how stingy he is with sharing electrons. He's just not going to do it. So you can't string any fluorines together here. They all have to hang off of the sulfur. So we're going to make 6, 1, 2, 3, 4, 5, 6, as far apart from each other as you can. Put your little fluorines in there. We have a lot of electrons to distribute this time, but hopefully you can start to see the pattern where these electrons go. So we've used up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, and you're all done. Sulfur has expanded valence. Okay, this one's a little bit strange because xenon is a noble gas, but fluorine is actually able to bond with xenon because xenon is such a large atom and fluorine is so small and so electronegative that he can take his electrons or share them. So xenon has 8 valence electrons, very, very uncommon for it to bond. Plus 4 times 7. So you'll have a total of 36 electrons in this case. Xenon will go in the middle. Spread out the fluorines. Okay, so we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We've used 32. We actually have 2 extra sets of electrons to put around here somewhere. So we're going to do that on the xenon. So you'll have 2 extra electrons here and here. Doesn't really matter where you put them. You can put them any place. But xenon has 2 extra. What do we call these little guys? Lone pairs of electrons. Okay, you'll use the same rules to draw structures for polyatomic ions. In addition to those rules, if an ion has a negative charge, like almost all the polyatomic ions, you're going to add that negative charge to the total number of valence electrons, and I'll show you what that means with an example. If the ion has a positive charge, you will subtract that number from the total amount of valence electrons. Because remember, if it has a positive charge, it actually has a less total electrons. Then we're going to draw brackets around the structure. We're going to indicate the charge on the upper right hand side of the brackets. That's where the charge will go, right in this little area. Here are some common examples of polyatomic ions. This is sulfate. Let's just write the name so we don't forget. So sulfur and oxygen are actually in the same column, and they both have 6 valence electrons. So this will be 6 plus 4 times 6. Then here's the difference right here. This overall has a -2 charge. You're actually going to add another electron to this whole structure. So 6 plus 4 times 6 is 24. Plus 6 is 30, plus another 2 is 32 electrons, which is divisible by 8, which is easy. So we're going to put sulfur in the middle. Oxygens will go around the outside. You know they're going to be bonded at least once, so we might as well just put that in there. So we've used up 2, 4, 6, 8. Time to sprinkle some electrons. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, and that's our total. The only thing that makes this different, besides the charge, is when you have an ion, you need to put the whole entire thing in brackets to mean this whole structure is included. You're going to put the charge of the ion on the outside. So this is going to be 2 minus for the whole structure. I want you to try the same thing for ammonium. Pause the video here and give it a try. Okay, nitrogen has 5 valence electrons plus 4 times 1 for hydrogen. This gives us 9 electrons, but remember, it's got a 1 plus charge. If it's positive, it actually means it's lost electrons, which are negative. So you're going to subtract that 1 back out of the system, so you get a total of 8 yet again. Nitrogen goes in the middle. Hydrogen's around the outside. Remember, hydrogens are only allowed to have 1 bond and no lone pairs. So look, 8 electrons, 2, 4, 6, 8, a piece of cake. Total of +1 charge for everything in the brackets. Let's see how much you remember from polyatomic ions. Pause the video and give each one of these their proper name. Okay, if you said nitrate and cyanide, you were right. Nitrate has an overall -1 charge. Nitrogen contributes 5 plus 3 times 6 minus 1 means it's got an extra electron in there, so we're going to add that in. So you really have 6 plus another 3 times 6, which is 24. Nitrogen goes in the middle. You have 3 atoms around it, so let's spread those out evenly. We'll need at least 1 bond between each. 2, 4, 6. Now, you may not want to draw this quite yet from here on. Just watch what I do. 24 total. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Seems okay, except we have a problem. Nitrogen in the middle here doesn't have an octet. He only has 6 electrons around. So remember when we solved that problem the last time, we had to make a double bond. So it doesn't matter which oxygen you take those electrons from. It makes no difference at all. I'm just going to pick the top one. And I'm going to take 2 electrons off of that and share it with the nitrogen. Now it really doesn't matter. In fact, this has something called a resonance structure, which we'll talk about in the future if you take AP Chemistry. But now we have 2, 4, 6, 8 around this oxygen, 8 around this one, 8 around this one, and 8 electrons around the nitrogen. You can go ahead and draw this. The whole thing will have a charge of -1. Pause the video here if you need to draw your structure. Okay, if you have 2 atoms, there's no central atom, so you put them right next to each other. So carbon has 4 plus nitrogen has 5, plus it has an extra electron in there for a total of 10. Put them right next to each other, C and N. Now, we're going to sprinkle our electrons. Again, you might want to watch me do this first. 2, 4, 6, 8, 10, 12, 14. 14? That's way too many. We only have 10 to deal with. Time to start pairing up. So let's take some electrons from each side and make a double bond. 2, 4, 6, 8, 10, 12. Still too many. Let's share another pair. 2, 4, 6, 8, 10. Here is the structure of a very poisonous chemical, cyanide. And the reason cyanide is so dangerous is it actually looks very similar to another chemical, which is really important in your body. You don't need to draw this, but this is what oxygen looks like. And these end up in the same place in your blood, which is why cyanide is so toxic, because it knocks out the oxygen.